Hey, Connor, are you done with the prototype?
Oh yeah, man, I'm almost done. Just give me a moment. Actually, why don't you follow me over here to the board and kind of show you how this whole thing works. Now, I call it the Sunny Circuit. Reason being, well, you're about to see. Well, now, I know what you're thinking. What the hell is this? Pardon me, but I will tell you in great detail momentarily. So this is a unique circuit, as you can see. Each capacitor is going to have a value of about... Oh, well, I guess someone's at the door.
Hey Collins, what's up, man?
What's up,
How's it
HASHAM?
going?
It's going great, dude.
What's going on?
Nothing much.
What you guys working on?
Actually, I think you might be able to help me. I was just trying to explain about the prototype that we're making, the Sunny DC circuit, and how each capacitor is going to have, set values which are uniform, value of 100 microfarads, and, we're going to break this bad boy down, find the equivalence capacitance, and the voltage that's going to be held throughout the entire circuit, as well as, each individual capacitor as well. As you can see, we went ahead and loaded up Sunny with some voltage, EMF being 12 volts, and it kind of came to life a little bit, made it a little toasty in here for some of us. Essentially, each of the capacitance on the capacitors will be 100 microfarads, respectively. Now, we have the EMF, which separates the top 4 capacitors from the bottom 4. What we're going to do is, in order to calculate the equivalence capacitance and therein the total capacitance of the entire circuit, we'll start by adding the top 4 and the bottom 4, respectively. Now, how would we do this? We're going to end up doing this in series. Now, if you look, each of these 4 capacitors on top are all in a series with one another. Now, how does one add together capacitors in series? Looking at the equation right here, as stated, we know that the equivalence capacitance of the capacitors 1, 2, 3, and 4 will have to be added inversely. So we have 1 over C1, C2, C3, C4 respectively, and each of them being 100 microfarads, we get 4 over 100 microfarads. Now we have to add that inversely in order to find the equivalence capacitance of the 4 capacitors. Doing that, we will simply flip that number, having 104, divide it, and end up with 25 microfarads for the capacitors 1, 2, 3, and 4. Now, respectively, we do the same thing with the bottom half of the capacitors in series on Sunny, and we take our calculations over here. We have the equivalence capacitance of 1 over 5, 6, 7, and 8. We do the same procedure that we did with the first 4 in order to get a total of 25 microfarads as well. You can see that we add each one of them, 1 over their respective value, getting a total of 4 over 100 microfarads, inversing it, and ending up with 25 microfarads. Now that we've added those up, the circuits will be parallel to one another. Except, how would we represent this, you ask? Well, I'll leave that to my cohort, HASHAM, to answer that for you.
Alright, now that we have the capacitance added in series, how we are going to represent them is like so. We're going to add all the capacitors 1, 2, 3, and 4 and represent it as one capacitor with a charge equal to the equivalence capacitance that we got over here. For this one was 25 microfarads, for that number right here. Same thing goes for the bottom one, capacitor 5, 6, 7, 8, and that's 25 microfarads. For that right there. Now the question becomes is that how can we add these two together? Because these two capacitors now are in parallel. And the equation we use to add capacitors in parallel is like so. The equivalence capacitance is capacitance of 1, 2, 3, 4 plus capacitance of 5, 6, 7, 8, which is 25 microfarad plus 25 microfarads, results into 50 microfarads. And that is the total equivalent capacitance of the circuit. Any questions?
Okay, now that you have the total capacitance, do you know how to find the total charge?
I don't know. Why don't you show us?
Alright, fine then. Follow me.
Okay, now that when we find the total capacitance, we can find the charge. So the equation for charge is Q total equals CEQ times EMF, which in this case our CMF is 12 volts, so we have 12 volts here, and our CEQ is 50 microfarads. So we multiply them both, and we have to change the 50 microfarads to farads, so that is 50 times 10 to the negative 6, and then we multiply that times 12, that'll give us the total charge, and it's 6 times 10 to the negative 4 coulombs. So we need to change it back to microcoulombs, which is 600 coulombs. And from there, we need to find the charge at each capacitor. So whenever it's in parallel, we need to use the ratio. In this case, the ratio it's 25 over 50, and it's going to be the same for both because the capacitance is the same. And the 25 we got it from the C equals 2, 3, 4, which we found out earlier in the series. And we divide by 50, which is the equivalence capacitance, and then we multiply it times the total charge, which for the first one, for the first capacitor, the charge is going to be 300 microcoulombs, and it's going to be the same for the second one because they're the same capacitance. And then we start again at the beginning, and we need to find out the total charge in each capacitance.
Oh, I'll take that! Thank you very much. Well, the charge on each capacitor. What do we know about charges on capacitors in series? Well, I will tell you. Capacitors in series have the same charge. Therefore, when we are adding in series, we can just go ahead and cancel this all out. Why? Because we know it's all going to be the same.
That lets us know that each of these capacitors, 1, 2, 3, 4, and so on and so forth, including 5, 6, 7, 8, will all have a charge of 300 microcoulombs. Now, we found the charge on every single capacitor, including the capacitors in series, utilizing the ratio of the capacitors in parallel, 25 over 50, 1/2, multiplying that by the total charge of the circuit, 600 to get 300 microcoulombs. Now, there's one thing that remains, and what could that possibly be? What is the voltage across each of these individual capacitors? Well, that's really easy. We know that in this entire loop right here, in the 5, 6, 7, 8 loop, from high potential to low potential, we have a total potential difference of 12 volts. Now, we can isolate one capacitor. We know that its value is 100 microfarads. We also know that the charge is 300 coulombs. The equation for charge and capacitance equals Q equals CV. We can easily rewrite that as V equals Q over C. So for this instance, we have 300 microfarads all over 100. I didn't say coulombs, I'm so sorry. 300 microcoulombs all over 100 microfarads. That, the micros cancel, you get a total of 3 volts. This lets us know that for each of these capacitors, we have a potential difference across them being 3 volts. This makes perfect sense because in one loop, we have 4 different capacitors, which means that 3 volts is distributed evenly throughout each one. Therefore, in our total loop, the addition of all the voltages across will equal 12 volts.
So now that we have all the theoretical data, let's go ahead and test it. Follow me.
We have this circuit set up right here. Each one of these capacitors is 16 volts and 100 microfarads. These capacitors right here, as you can see, they're connected in series. However, there's a loop right here, and there's another loop right there. These loops are connected right here to the DC voltage, which is 12 volts. As you can see in the voltmeter, we have 12 voltage going across our circuit. These capacitors, this loop right here and this loop right here is connected in parallel. However, these capacitors and this loop are connected in series. And next step we're going to do is we're going to show you the voltage measured across each one of these capacitors, and we're going to see if this matches the theoretical value.
So as you
As you can see with the capacitor number 1, it's 2.72 volts. With capacitor number 2 is 3.11 volts. Zoom into this one. For capacitor number 3, it is 2.99 volts, so close to 3. And for the capacitor number 4 right here, the voltage is 3.20. Alright guys, so now we're going to measure the voltage across the capacitors on the other side of the loop. This is capacitor number 5. As you can see, the voltage right here is 2.97 volts. I'm going to disconnect this and connect it to the next one. For capacitor number 6, the voltage is approximately 3.39 volts. For capacitor number 7, the measured voltage is 2.19 volts. And for capacitor number 8, the voltage is 3.5 volts. As you can see that all these capacitors have the same voltage, maximum voltage in same microfarads. However, you saw the difference in the values, which could explain the error. Maybe these wires are broken off or something is going on with those. That's one of the things, one of the errors. The other errors, we can discuss that later. Alright guys, now that we are done with the experiment, let's go ahead and review the values that we got. Our theoretical value was supposed to be 3 volts across each capacitors, but when we measured it, we got these values. And you can see from the first loop, this is the first loop right here, when you add these values up together, it roughly is equal to 12.02 volts. And same thing about for the second loop right here, it comes out to be 12.05 volts. And all of these values are roughly close to approximately 3 volts. Some of these values are way off. The reason for that, one of the reasons could be like the cracks in the wires, unstable battery feed, or like accuracy of the capacitor itself. Depends on was it charged already or was somebody just using it before we started using it. You know, those sort of things. And also some of it has to do with the accuracy of the voltmeter.
So, boys, I believe we learned a great deal today, thanks to our prototype, Sunny. Tell us about the relationship of capacitors and whatnot in series.
Yeah, we learned how to add capacitors in series and parallel. And also from there we can learn about the charge.
Yeah, once we find the total capacitance, we can find the total charge, and from there we can work backwards to find the charge in each capacitor.
Yeah, that's amazing. And we also went out and tested, and we saw that the voltage was approximately the same across each capacitor.
You know, looking at the circuit, Sunny, everything seems like a lot to take in. But as a great Dr. Store once told us,
Complicated things are a bunch of many simple things put together.
Thank you so much. Have a good day.